higher gradient methods, and title has changed, obviously, variational methods. So it has to do something with the tetrahedron argument.
Okay, but I will tell you. Also, this title is changed. Okay.
You expect a very nice talk, and please go ahead.
Okay. I remarked this morning that something which has been explained to me when I was a student at the University of Napoli several years ago is still true, and maybe it is even more true, is more and more true. There is a big gap between what is done by theoretical physicists and people working in statistical mechanics and what is done by people working in continuum mechanics. My professor, my laurea master degree is in physics, and I studied theoretical physics with Professor Stroffolini in Naples, and he was shouting in a typical Neapolitan way against this crazy division between two ways of thinking which should be always present in the mind of physicists. He was giving us a talk about models, atomistic models and continuum models in physics, and he wanted in his lectures to underline that you need to use both of them in different situations if you want really to model reality. This morning, while my friend and colleague Pierre Sepecher was trying to tell here what we believe to have done new in a small part of continuum theory, we understood that actually if we want to communicate, as we believed it is necessary, to people in this audience, something I need first to tell you some more details about some aspects of continuum theory, and these details are essential in order to let you appreciate what we are trying to communicate to you. This is a first observation. Second, I enjoyed some of the talks because of the typically physical way of describing things and phenomena. So maybe I will change also a little bit my plans, and I will try to show you how second gradient models can describe how a sponge is deformed, in order to let you see that what our presence in this conference is not casual. We also are trying to study some anomalous transport phenomena, in particular the flow of a fluid in a porous medium, and how the deformation of this porous medium is influencing the flow of a compressible fluid inside this porous medium. Okay. Variational principles play a role in this effort we are trying to do. So I was thinking to talk a little bit about how these methods are applied in continuum mechanics, but as I told you, I need to change a little bit the plan of my talk. Of course, I believe it is better for the few people who are here now, it is much better if I tell you something which has not been invented by me, because, by the way, I don't believe to have invented too many things, but instead of going to show you the comma we have added in a theorem, it is better if I try to give you a large view of continuum theory and continuum mechanics, and then to tell you which are the difficulties we needed to solve and attack in a given moment. Then maybe we will have time to talk about the comma we were talking before. Okay. There is a long story of continuum modeling in physics and in mechanics, in engineering sciences. I strongly suspect, after the lecture of Professor Russo, that this story is very old. However, I have evidence, because the Comptes rendus de l'Académie des Sciences de Paris are available, and you can read the French in which they are written rather easily. It's not like Greek. By the way, I want to underline that Professor Russo is one of the few persons in the world who is able to read mathematical Greek, understanding what is written in. Okay, so. And Metrodon, however, Metrodon I translated myself, but this is another story. I will tell you later. Navier, à l'École Polytechnique, wanted to teach the theory of beam. And he wanted to study the theory of deformable bodies. Why it is important to remember here now Navier? Navier attacked the problem using the atomistic theory. He imagined a beam as a set of atoms with springs, and starting from the equation, Newton equation, force on every atom equal mass of this atom times its acceleration, tried to deduce the theory of deformable bodies. Useless to say, for many decades after Navier's effort, people were talking about the famous Navier mistake. In averaging the equations, he did several mistakes, and he got a continuum theory which is wrong. Okay? Now I have spoken with several specialists in statistical mechanics. There is no available deduction of the theory of solids, deformable solids, starting from an atomistic theory. On the other side, and there are field medals which were recently assigned, Boltzmann equations and all that theory allows people to deduce rather efficiently the theory of Stokes-Navier equations for fluids. So while the statistical procedure, which starting from atoms leads us to continuum theories for fluids, is actually available, we must say that there is no theory for deformable solids. A fortiori, there is no theory for a porous medium full of a deformable fluid. And this deformable fluid, while flowing, deforms the solid matrix. So, either you decide to try to generalize Boltzmann equations somehow to attack a very difficult problem in statistical mechanics, and I don't believe to be so strong, or you use Cauchy method. Because you can try to design a wing of an airplane or to study how a sponge is deformed using the theory of atomistic theory and quantum mechanics. However, it is so far from the last equations you need to use that maybe one can start from a macroscopic theory directly. However, as Pierre Sepecher was proving you this morning, when you have a complex macroscopic system, balance of force is not enough for finding the equations you need. I strongly suspect that this problem was already present in ancient science, but again, let us forget about this. Euler used a variational principle for deducing the equation of a deformable beam. Lagrange used a variational principle for deducing the equations of a compressible fluid, and Lamé and Maxwell studied in a greatly detail the waves propagating in a perfectly deformable solid they called ether. They even arrived to say that the solid which is best known is the ether, because you can measure Lamé coefficients of ether in a very good way, okay, if you measure the speed of light, okay. They studied this body using a variational method. While deducing the equations for this deformable body, Cauchy met, after an integration by parts, a force per unit area. So, imagine you postulate that a body has a kinematics. The kinematics of a deformable body is a function of 3 variables which label every material particle of the body, and another variable which is time. This is called placement and gives you the function which maps to every material particle its position in a given instant. Okay? Having this function, you can measure the deformation of every small infinitesimal cube of this deformable body, and you can introduce a deformation energy for this body. So how can we find the evolution equations for such a system without going to the depth of atoms? You can postulate that nature minimizes something. Nature is minimizing kinetic energy minus deformation energy and some external conservative force. So let us start thinking about conservative systems for avoiding discussions which may be dangerous. So what you do, you take your energy, okay? You add deformation energy, you add with a minus sign kinetic energy, you calculate first variation of action, and you find bulk equations, and with an integration by parts, you find boundary conditions. Now, all this is available in books. Everybody, open Gallica. You know, French government is letting everybody access these original papers they gathered in Gallica. They meet an animal, the result of integration by parts, and they remark, oh, this animal is a force per unit area. Okay? When you arrive at this point, you are led to say that there is a contact force on this surface, which is a force per unit area, and this force represents the action of one side of the body on the other side of the body. This interpretation is due to Navier. He was teaching this at l'École Polytechnique to the students, his students of engineering. Okay. Now, Cauchy starts from this point, he refrains, he doesn't want to use variational principles, and he starts from the idea that we have a deformable body. We imagine to cut it in two parts using a surface. From that moment on, such a surface has been called Cauchy cut. And removing in your imagination the part of the body on one side of this surface, you imagine that this removed part acts on the remaining part by means of a force per unit area. This is called Cauchy density, surface density of force. Okay? Now, the question is the following. If your system is microscopically heterogeneous, this assumption by Cauchy is false, in the sense that the action exerted from one part of the body, the one you have removed, on the part of the body which is there, this action cannot be described simply by a force per unit area. To be more precise, I am talking in a way which French people don't like completely. So to be more precise, let us talk about energy transmitted during the motion from one side to the other because of the deformation. So you consider power expended, transmitted by one part of the body to the other. Okay? This power cannot be expressed in terms of inner product of a vector times velocity integrated on the Cauchy cut. You need to add at least the integral on the surface of something times the normal derivative of the velocity. Then, if you were lazy and your Cauchy cut has some edges, so it is not smooth, so you have the normal which is jumping through this edge, then you need a force per unit line. That is something which is expending power on the velocity of the material particle which is on this Cauchy cut. But this is not yet ended. Unfortunately, or fortunately for us, we could add some commas to this story. What happens is that if your surface is curved, so Gauss curvature is non-vanishing, the normal is not constant, so you don't have a flat Cauchy cut, but you have a curved Cauchy cut, the surface per unit area does not depend only on the normal. It depends also on the gradient of the normal, that is, on the curvature of the Cauchy cut. Okay? Several people in several moments discovered some piece of this frame. In my opinion, the first one who has understood completely the frame was Paul Germain. But one could argue that maybe Midlin or Tupin or somebody else understood this way. But the important thing is that in the 60s, this frame was completely understood. I want to underline several things. For instance, there are people in plasticity or in granular materials who are trying to estimate the contact force inside a deformable body, estimating some averages. So they consider the interaction between the material particles of the body, they do some calculations, and they very often discover that the Cauchy stress, that is the linear map which maps the normal to the surface to the force per unit area, which is the contact force in the Cauchy theory, this Cauchy stress does not depend only on the deformation of the body, but also on the gradient of this deformation. Okay, so they add this dependence, but they don't add, for instance, edge forces, or they ignore the dependence on the curvature. So the theoretical effort which is needed, in my opinion, to give the right model is important, because otherwise you risk to develop a model which is without one leg. You add one ingredient, you don't add the other ingredient, and then you find paradoxes. I want to say, for instance, there is a beautiful paper by Serrin and Dan. They study second gradient materials. When they write the balance of energy, they discover that there is a missing term. They cannot get balance of energy. So they add, rather artificially, another flux of energy, which they call interstitial working. So out of the blue, they add in the balance of energy an extra flux of something which is needed in order to have balance of energy. Okay? This is again needed if you don't have a clear frame. Okay? Okay, so after having said this, maybe I can quickly review the result which you find both in books of mathematical physics and in books of continuum mechanics and even in Landau. You know, Classical Field Theories of Landau is a book in which you find written in a way or another these ideas. Okay, again, this is to prove that I can type in Greek at least. Now, the problem is the following. I have some kinematical descriptors. I have the time variation of these kinematical descriptors, which we call motions. We postulate some action functional, and we assume that nature wants to minimize this action. Now, why it is very wise to use this approach?
Comment. My question of this morning wasn't so tragic to require the whole history of it. Was much simpler. I mean, we don't believe that the atomistic description, matter is made of atoms, okay, we believe that. We don't believe that our description of the atomistic level can be taken to describe everything that is in the universe. There are various levels of applicability. So, I wasn't criticizing the use of continuum.
No.
I asked, because as statistical mechanicians, if we can put that way, I would say that our job is that of devising toy models, which, however, teach you something, you know, and the easy model is perhaps the best known, okay, but we continue to do that in order to understand certain principles in the simplest possible form. So we use idealized models of this situation or of that situation. And so my question was, what is the motivation for considering the rigid body is it the same as I would see another toy model in statistical mechanics, or there is another motivation? And I make a parallel with hard spheres, saying, look, even hard spheres is a strong idealization, but we use it for certain purposes. For instance, because about hard sphere models, it is possible to prove certain results which in other settings you cannot. Okay, so this was the sense of my of my question. Okay? I wasn't saying all the atoms are there, so how do you get
but rigid, the example of rigid.
Then variational principles are one of the fundamental things that are used in physics at large. Okay, so not necessarily. So certainly I understand that they are useful. That is not another problem. And then continuum mechanics, we do here in the statistical theory of fluids, and they are continuum. And when you read these fluids, but they are not necessarily rigid bodies. Okay, so you understand now the meaning of my question.
But this was not the answer only to your question. First of all, the example of rigid body was there simply to tell you that even in the very simple case of a rigid body, force is not enough and you need to add a couple.
Yeah, okay.
So, a fortiori, if you have a deformable body, you cannot expect that forces are alone sufficient for describing the story.
Yeah, but then this is the answer.
Maybe you just continue and ask questions later on. I think you have now understood the motivation of the before.
So but I will continue to comment about this. Action is minimized if you use atomistic theories and if you use continuum theories. So, if you are lost in the averaging procedure, so you do not know if you want to use micro-canonical, grand-canonical, or every averaging procedure, and you are afraid to follow the destiny of Navier and to do something which is wrong, then you are left with the only thing which for sure must be valid. So this is an heuristic strategy. Okay. However, and I close the bracket, frequenting too many French people for too much time, I started to believe that everything is minimization of action. But this is my problem in a sense. Okay? So, I want to clear up, because this is how we proceeded in finding our original results. First of all, you need to focus to which class of systems you want to describe. Because Cauchy model is very good if at a microscopic level your body is homogeneous. So you need to focus on what you want to do, which kind of phenomena you want to describe. When you have fixed this, then you introduce what mathematical physicists call configuration. That is the mathematical model of the state of the system. Then you have a time function, which is the motion, and then the action, which is a real valued function, which models what has to be minimized. So, in my opinion, you need to keep always in mind that you have two different worlds, reality and the model. And the configuration is a model of the state of the system. So, for instance, if you have your body, the state of the system is something real. Then, if you use continuum mechanics, you describe the state of this body by means of a function. If you use atomistic theory, the same body you describe with a set of positions of all atoms you have. So you have different configuration spaces for the same system and the same state. You have the motion which models evolution, and motion minimizing action which model observed evolution. This frame is good both in continuum mechanics and in atomistic mechanics. So you cannot be too much wrong if you use this scheme. Okay? Now, here I can go quickly. Of course, if you want to minimize a function, you need to say which is the domain where you are looking for minima. This is clear. Minimizing a function means that you need to know where it is defined, and when you have fixed the domain of this function, only then you can look for minima. If you change the domain, the set of minima can change dramatically. So the most important thing is to clear up what is the admissible kinematics. Okay, Maupertuis calls the utility to be minimized or maximized action. Okay, and then, but this now is clear. When you specify the accessible motions, then you need to minimize action there. To make it clear, but I've seen it doing this morning, so this question is clear for everybody. Lagrange is fixing starting time instant and ending time instant, the configuration at the first instant, the configuration at the end, and then it minimizes in this set of admissible motions. So I think that on this we agree. Now, my suspicion that this idea is very ancient comes from the fact that Olympiodorus says in a given moment for doing a proof of a theorem that this would be agreed by all, that nature does nothing in vain nor labors in vain. And this has been rephrased by Pierre de Fermat. Okay, now this idea you find in the mécanique analytique. Of course, you need to learn which are the infinitesimal variations of motions, what is a differential of a functional, and what means that an infinitesimal is of order greater than 2. But I think that this is all clear. So, I simply show you this. You know, this is typically French. La nature se dévoilant à la science. Musée d'Orsay. Only in France you find a faculty of science with a statue like this. Okay? Now, if you want to unveil nature, find a Lagrangian. This is my advice. Now, this I will do it quickly, then I skip to the practical problem, which the mathematical description of which I will try to show you tomorrow. This you find in Landau. So this is pure physical orthodoxy. Okay? You have an action functional depending on, so we are in 4 dimensions. X means space-time variables. Psi sigma is a set of tensors, vectors, scalar fields, depending on what you want to do. D over dx mu of these fields is their gradient. Then you write the action functional. You calculate the variation of this. You do, a Taylor expansion. You simplify in your higher order infinitesimals. You integrate by parts. And then you get this bulk equation, which you get from arbitrary eta. So this is the result of the particular form of principle of virtual powers in this aspect. And you get, okay, in space-time this becomes this animal. And okay, here I remark explicitly that this first variation is equivalent, is not equivalent. It implies a particular form of the principle of virtual powers. Okay? And then I have not written boundary conditions. Okay, I will show you in another slide. Here I discovered, because I was attacked, there was not a friendly question as yours somewhere. I was attacked. People said that least action is different from the principle of virtual works. The reasoning you find in Landau proves that if you have an action, you calculate its first variation, you get a particular form of the principle of virtual powers. So you may say that you want to be more general. You cannot say that least action is different from virtual powers. Okay. Last thing I want to tell you, but also this is well known by physicists, you can add a Rayleigh dissipation functional if you want to introduce in the scheme dissipation, and the first variation of Rayleigh functional equated to the variation of action gives you the evolution equations. Now I must try to find the file with the physical problem, which the equation of which we will discuss later here. Okay. So we said that what is ball M? No, I've done something wrong. Okay, it is enough. So the problem I want to solve, this is the kind of problem, practical problem, which is paralleling this context, this nice problem of ocean motion, for instance. So you have a porous medium. You apply a force on the solid matrix. Okay. The fluid in the porous matrix, in the porous medium, can flow because pores are interconnected. So you can have a Darcy type or a relative motion of the fluid with respect to the solid. And you want to understand how this system is deformed by the application of this weight at the top of it. Okay. If you do, you add second gradient terms, so you consider an energy which is not depending on the deformation, but also on the gradient of the deformation. We will talk in detail about this mathematics tomorrow. You get a set of, in the case of one-dimensional consolidation, you get a set of differential equations in the only space variable and time. Okay, and we will discuss this in details. You get boundary conditions with the reasoning, the integration by parts. Okay, and then you are able to solve an apparent paradox of the classical theory, which I will describe you quickly in the few minutes I have left. When you have this consolidation problem, you have a singularity at the initial instant of time, because you have the fluid density in this porous matrix, which you can imagine to be constant. Then you apply at a given time instant a load, Okay? So if you write the equations, which in the original form are exactly diffusion equations, which is regular transport, not anomalous transport, okay? Then you are in troubles, because the boundary condition at instant t equals 0 and all subsequent instants is a given value of density. Okay? Then the initial condition for density is a different value. So at the boundary, the classical model without second gradient becomes crazy. If you try with a Gagliorchin method and you use 200 elements, okay, still the solution is that crazy wave you have there. Now, walk on the beach. If you place your foot on the sand, you discover that an important boundary phenomenon occurs there. In the classical theory, there is no mean for describing this boundary phenomenon. Okay, of course, we need to develop a microscopic theory at a given level, maybe at the level of pores, not at the level of atoms, for understanding better what happens in this boundary layer. However, if you simply add second gradient, of course we introduced big energies related to second gradient in order to see better, in a better way, the boundary layer, okay? Then the boundary condition is regularized, and you can see in red the profile of density in this, or pressure which is equivalent in this layer, and you can compare it with the classical solution. What is amusing, and then I will really stop, is that this model is forecasting a new phenomenon. We may need to try to conceive an experiment to see if this phenomenon is real or not. At the bottom of this sponge, I didn't say it explicitly, but at the sponge we assume there is a impermeability condition, so there is no flow. You have, in second gradient model, you forecast an overpressure. So the graph of the density or pressure is increasing at the bottom with respect to the initial value. So at the depth of this sponge you have this effect. Then in time everything is regularized, and this is the decay of the field. Okay, of course here there is a dissipation. The dissipation is related to the relative motion of the solid with respect of the fluid, which is a standard Darcy dissipation. Okay, so what I will try to tell you tomorrow is how, in more detail, you can get these results, but I hope that I can be of help in letting you appreciate the lecture of Pierre Seppecher, because he wants to tell you how continuum mechanics has to be improved, classical Cauchy continuum mechanics has to be improved in order to describe this boundary phenomena, for instance. Okay?
Thank you very much.